Another important chemical property of soils is cation exchange capacity. Now, we talked a little bit about cation exchange capacity before, but we're going to re-emphasize some of the key points and why it's important for soil functioning. Essentially, in soils, there are weak electrostatic interactions. And we talked about how on the surfaces of clays, for example, there are often positive charges or negative charges, and these negative charges attract cations, which have a positive charge, and the positive ones anions. Now, when there's more negative charge to materials than there is positive charge, you have a net cation exchange capacity, but soils are going to have the ability to exchange both anions and cations. One of the important things when we talk about cation exchange capacity, for example, is base saturation. And base saturation is the percentage of the total exchangeable cation pool that is accounted for by base cations. So remember that protons are a source of positive charge in soils, but so are cations like calcium as well as potassium. And so if you take a look at the ratio of positive charge that's associated with cations as opposed to all of them, cations and protons, then you have a situation where you can start to calculate your base saturation. So essentially, how much acidity is there that is taking up cation exchange capacity as opposed to cations like calcium or potassium? This is important because soils need to have buffering capacity for good functioning. And buffering capacity is the ability that once cations are taken out of soil solution, for them to be resupplied by the soils themselves. And when you lose that buffering capacity, one of the things that happens are some of the cations that are very difficult to remove from cation exchange capacity begin to leach out. One of the most important ones is aluminum. And aluminum is one of those, we'll talk about this a little bit, but it's one of those cations that are very difficult to displace. And once you just start to displace it, then you're starting to generate toxicity. And aluminum in this form is toxic to a lot of organisms. Now, when we think about cation exchange capacity, we talked mostly about clays, for example, and we talked about how there are 2-to-1 clays and 1-to-1 clays, and clays have different amounts of cation exchange capacity with them. But it's also important to recognize that organic matter has cation exchange capacity, because all you need for cation exchange capacity is to have a net negative charge. And in organic matter, you can have this, which when you lose your protons, generates negative charge. And so organic matter is a source of cation exchange capacity. In tropical soils that are very highly weathered, the clays don't have much cation exchange capacity. It's really the organic matter that generates most of the cation exchange capacity in soils. Cations occupy exchange sites and displace other ions in sequence. So this equation 3.5, shows that sodium tends to occupy exchange sites, but be one of the first cations to be displaced. After that, you have potassium and ammonium that gets displaced next, and then magnesium and calcium. So if we had a relatively young soil that had all these cations in it, and we started adding acid to it, for example, and there was a source of protons, it would first kick off the sodium, and after that, ammonium or potassium. And these would be the first to be displaced from exchange sites on down the line. Another thing that's important to realize is that by the time you've displaced most of these cations, all that's left are additional protons to displace, and then aluminum. And the reason why that's important is aluminum 3+ is toxic. Now, the reason you get this sequence has to do with charge, and it has to do with radius. And essentially, the more charge you have, or the smaller your radius, the more tightly bound you are to an exchange site. So sodium, for example, monovalent, relatively little charge, but also a relatively large radius. and that's pretty easy to displace compared to something like calcium, which has more charge and a smaller radius. Now, in addition to cation exchange capacity, soils also have anion exchange capacity, and as we talked about before, some soils actually have net anion exchange capacity, can exchange more anions than they can cations. Now, just like there's a sequence of displacement for cations, there's a sequence of displacement for anions. And in this case, nitrate is one of the first anions to be displaced, followed by chlorides and then sulfates, and lastly, phosphates. And so again, we have relatively little charge and a large radius, and by the time we're down to here, that ratio changes and you're going to have a lot more charge and sometimes a smaller radius too. By the time we're down to phosphate, we're really involved in not just electrostatic interactions, but there are also strong chemical interactions that occur. And phosphate is one of those compounds that really can become more tightly bound and actually undergo covalent bonds and chemical interactions with soil particles. Once that happens, it's really hard to displace phosphate into soils and make that available to plants. This general process we refer to as fixation of phosphorus, and that's a covalent bond of phosphate to another chemical that makes it readily unavailable to plants.